Welcome all my dear students to Sudharma's physics classroom. Today we are going to do the question answer part from the chapter magnetic effect of electric current. So let's assess what we have learned. So let's start from the question number 1. A current is passed from south to north through a conductor placed below a freely pivoted magnetic needle. To which direction will the north pole of the magnetic needle turn? Which is the rule used to arrive at this inference? State the rule. If the current flows in the conductor in the east-west direction, what do you guess about the deflection of the magnetic needle? Explain. So let's start doing it one by one. It's a big question, right? So the basic thing we need to understand is if you keep a compass needle without the influence of any other magnetic field, it aligns in the north-south direction. So that happens because of the influence of the Earth's magnetic field. Now what we are going to do is, we are keeping a current carrying conductor below this compass needle. And the question says that the current is passed from south to north. Okay, so here the conductor is kept horizontally and the direction of current is from south to north. So in which direction the north pole of the magnetic needle turn? So we know that when we have to find out the direction of magnetic field, we have to use right hand thumb rule or corkscrew rule, right? Maxwell's corkscrew rule. So when we apply the rule here, just try to apply, hope all of you remember this right hand thumb rule. Thumb in the direction of current and the other fingers, the wrapped fingers around the conductor will be giving you the direction of magnetic field. So if you apply that, the magnetic needle is kept over this current carrying conductor, right? So we see that the magnetic field lines are into, right? It's going to be, it's just when you try that, your curled fingers will be trying to pierce this paper. So we can say that the compass needle's north pole will be moving towards the east direction. So answer of question A is towards east. Towards east. But when we apply this right hand thumb rule, it is little bit difficult to answer this question, because which direction, we can say that either the magnetic field is into the plane or out of the plane, right? But in which direction the compass needle deflect? For that, we have a very easy trick, that is Ampere's swimming rule. This is very easy. It's Ampere's swimming rule. It states that if a man swims along the current carrying wire such that his face always face is always towards the magnetic needle through which the current is entering his feet and leaving from his head, then the north pole of the magnetic needle is always deflected towards his left hand. So it's very simple. So we are going to take a person who is going to swim in the direction of current. So as per our question, the current is from south to north. So this person is going to swim in the direction of current. So whenever we apply Ampere's swimming rule, the person has to swim in the direction of current. Now the two situations we can face is either the compass needle is above the wire or below the wire. So let's go back to this question. This question is, the conductor is placed below a freely pivoted magnetic needle. Okay, so conductor is below the needle, below the magnetic needle. So what happens is, when you take apply Ampere's swimming rule for when we keep the conductor below the compass needle, we have to keep the face of the swimmer upward. Okay, so normally how do we swim? We will be facing towards to the downward direction and swim, right? But this situation is, the conductor is below the magnetic needle, so we have to take the person who is swimming facing the upward direction. His face, we will be able to see his face if he is swimming. Okay, so in that case, in whichever direction his left hand turns. So here the person is swimming in this direction. Imagine the person is swimming in this direction. His left hand is this, right? So left hand will be towards this direction. So this is north, this is south, this is west, and this is east. Okay, so this is how we find it out. Suppose the case is the conductor is above the magnetic needle. If it is kept above the magnetic needle, then we have to imagine the person swimming looking downward. So in that case, in which direction his left hand moves, that will give you the direction of compass needle deflection. Understand the difference between Ampere swimming rule and right hand thumb rule. Right hand thumb rule gives you the direction of magnetic field. This Ampere swimming rule is a very easy trick to find out the deflection of north pole of the compass needle, because especially when the situation is magnetic field is into the plane or out of the plane, we will not be able to predict. It's not easy to explain in which direction the needle moves. We can simply say that verbally, we can say that it deflects the magnetic field direction, we can explain. But in which direction the needle moves, that we can find out using Ampere swimming rule. So once again, if the person is swimming in the direction of current, the person has to swim in the direction of current. If the conductor is below the compass needle, the person will be facing upward and swimming. So in whichever direction his left hand points, that will give you the direction of north pole of the compass needle deflection. So here the needle will be deflecting towards this direction, that is nothing but east direction. Okay, that is how we can find it out. But when you answer it here, there is no Ampere swimming rule explained in our textbook, right? Because another thing is we cannot go beyond our textbook. This is a trick for you to find out the direction. Okay, but we have to write and explain the right hand thumb rule for the question B and C, which is the rule used to arrive at this inference and state the rule. You have to state the right hand thumb rule. Now, if the current flows in the conductor in the east-west direction, what do you guess about the deflection of the magnetic needle? Explain. The current is in the east-west direction. So in that case, if the current is in the east-west direction, we know that here easily we can apply our right hand thumb rule. So this is our east to west direction. So initially where we kept this compass needle is pointing the north direction, right? From there, when the current was from south to north, then the deflection was towards the east direction. Now what happens? Now we have the current in the east to west direction. So in that case, we are going to apply our right hand thumb rule. When the current is in the upward direction, there will be an anti-clockwise magnetic field, right? When anti-clockwise magnetic field means the compass needle will be moving towards north direction, but the compass needle is already in the north direction. So this is how we have to find it out. Okay, so compass needle is already in the north direction. It's already pointing in the north direction initially because we kept the conductor in that way, right? And if there is no other magnet, then definitely the compass needle stays in the Earth's magnetic field direction, that is north-south direction. So already it is in the north-south direction. Now what happens when current is from east to west? We get an anti-clockwise magnetic field, but the compass needle deflection is towards north. So already it is in the north direction, so there is no deflection seen in the compass needle. That is the answer for the first question. Now let's move on to the second question. How will you determine the polarity when current is passed through a solenoid? Suggest methods for increasing the strength of the magnetic field around a current carrying solenoid. So this already we have discussed while discussing the chapter. So to determine the polarity of the solenoid magnet, we can use clock phase rule. So according to clock phase rule, if the current is flowing in the clockwise direction, that side will be the south pole of the magnet, and if the current is in the anti-clockwise direction, that is the north pole of the magnet. How will you increase the strength of the magnetic field around the current carrying solenoid? So if you have to increase the strength of the current carrying solenoid, increase the current, right? Increase the number of turns, insert a soft iron core material, right? And take a coil, take a solenoid of smaller radius. These are the methods to increase the strength of the magnetic field due to a solenoid. These are the things already we discussed during the classes. Now going to the third question. The figure shows an insulated copper wire AB made into a coil. Suppose the current flows from A to B through this. What will be the direction of electron flow through it? What will be the direction of electron flow? Okay, so current flows from, suppose the current flows from A to B. Current flows from A to B. If the current flows from A to B, then the direction of electron flow is from B to A. This already we have studied in electricity chapter. If the direction of conventional current is opposite to the flow of electrons, that principle is used here. Can you find out the direction of the magnetic field around the conductor AB? State the rule that substantiates this. Can you find out the direction of the magnetic field around the conductor AB? Of course, we can find out the direction of magnetic field around the conductor AB. We can use the right hand thumb rule. Right hand thumb rule, if you use in each and every point of this conductor, you will be able to find out the direction of magnetic field. Explain how you can find out the direction of magnetic field inside the coil. So you can look at this figure. If you apply this right hand thumb rule at any part of the conductor, you will find out the direction of magnetic field, right? So since it's a circular coil and the current is flowing in the clockwise direction, you can see that within the coil, always it is into the coil, right? So the magnetic field inside. Can explain how you can find the direction of magnetic field inside the coil, right? So inside the coil, the magnetic field is always into the coil. It's always entering into the coil. So how do you find it out? You have to apply right hand thumb rule at each and every point on this conductor, and you will find that your curled fingers around this conductor will be pointing into the coil, inside the coil. Okay? Or we can say that the magnetic field lines will be reaching to that coil. It will be entering into the coil, right? So that means that it is towards the south. So how do you find out the polarity, right? So the current carrying circular coil acts like a disc magnet. It has both south and north pole. So we know that in a bar magnet, when the magnetic field lines are coming into a side, that is the south pole, right? Entering into, right? That is into, if the magnetic field lines are entering into some side, that is the south pole of the coil. So into the coil or towards the south pole of the coil. Okay. So this is how we find out the direction of magnetic field inside this coil. So that side will be the south pole of the magnet. Hope you understood that. Let's move on to the question number 4. The magnetic field around the current carrying conductor AB is depicted. So AB is shown here. Based on Maxwell's right-hand corkscrew rule, find out the direction of current and record it. Based on Maxwell's right-hand corkscrew rule. So what is right-hand corkscrew? Right-hand corkscrew is the one which we can tighten the screw if you rotate it in the clockwise direction towards right. So we are going to tighten the screw in whichever direction the current flows. But here they ask the question in a reverse way. So they gave the direction of magnetic field. We have to find out the direction of current. So let's see in which direction if the current flows, we get this kind of rotation. We have to tighten the screw. Suppose I'm just giving you some ideas how to find out this. So then after that we can come to the answer. So if you are taking the current from A to B, that means I have to tighten the screw in this direction, right? So if I have to tighten the screw in this direction, just see, imagine or just take your pen, imagine that as a screw, and you're going to tighten the screw, rotating it clockwise using your right hand. So you see that the rotation is in this direction, right? But it is not. The question is in the other way. So let's see if you tighten the screw in this direction. So this is the direction of current, right? This is the direction of current. I have to use this screw and tighten the screw towards this direction. So I have to rotate it clockwise. So when I rotate it clockwise, you see that this direction is going to be as shown in figure. So the current will be in the direction B to A. Hope you understood why it is not from A to B. If it is from A to B, then it is going to be the opposite way, magnetic field direction. We can check the answer based on right hand thumb rule now. If you are applying right hand thumb rule, if you keep your thumb towards the direction of current B to A, then the magnetic field will be into the plane, right? So current is definitely from B to A as per this diagram. Okay. So moving on to the fifth question. Electricity flows through a very long solenoid. Some statements are given below related to the magnitude of the magnetic field developed. Find out the correct ones and write them down. So it says that it is 0, it will be the same at all points, it gradually decreases towards the ends, it gradually increases towards the ends. So this is how the magnetic field due to a solenoid looks like. It's exactly that of a bar magnet's magnetic field. And we have learned a special property of magnetic field within the solenoid. We can see that all the field lines are equidistant and parallel. We call it as uniform magnetic field, right? Magnetic field within the solenoid are uniform magnetic field, and it will point from south to north. But in the question we have to find out from the option. So uniform magnetic field means what? Uniform magnetic field means the magnetic field is going to be the same at all the points. But when you look at this figure outside it is different. But mainly when we talk about the solenoid's magnetic field, it is surrounding that, right? Through the solenoid, what is the magnetic field? So we can say that it is same. It will be the same at all the points. It's uniform magnetic field. Okay. Now moving on to the sixth question. The direction of movement of electrons through a magnetic field is depicted. The force felt by the electrons due to the influence of the magnetic field is into the plane of the paper. Is this statement correct? Explain based on Fleming's left-hand rule. So direction of movement of electron is shown, and the magnetic field direction is also shown. So we have to say whether the statement is correct or not. So what is Fleming's left-hand rule? If you take your left hand, thumb, forefinger and central finger mutually perpendicular to each other such that the forefinger indicates the direction of magnetic field, central finger indicates the direction of current, and the thumb indicates the direction of motion of the conductor. So here the direction of motion of electron we have to find out, right? Force felt by the electrons due to the influence of the magnetic field. So if you say the electron is moving downward, let's say this is the direction of magnetic field as per the diagram. Electron moving downward, that means the direction of current is in the upward direction. Okay, so this is magnetic field and this is current. So we have to keep all the three fingers mutually perpendicular to each other. So what happens? Then the thumb will be moving this way. This is motion. This is how we represent three mutually perpendicular axes. Now, what you have to do is you take your forefinger in the direction of magnetic field as per the diagram. So, we make sure you are using your left hand, magnetic field towards your right, and the current, central finger should point upward. So, you can see the thumb will be moving downward, right? Downward in the sense it is into the plane. So, we can say that the motion is into the plane. And the statement is correct. Okay, is the statement correct? Explain based on Fleming's left hand rule. The statement is correct because when the field and current are as per this diagram, as per the situation, the thumb will be pointing into the plane and the statement is going to be correct. Hope you understood this. In an experiment to know the intensity of magnetic field around a current carrying coil, why is the coil kept in the north-south direction? In an experiment to know the intensity of magnetic field around a current carrying coil, why is the coil kept in the north-south direction? So, basically the Earth's magnetic field, right? Earth's magnetic field will be in the north-south direction. the compass needle will be pointing in the north-south direction. If you keep this coil in any other direction and if you use the same compass needle, that may affect the result of the experiment, because whenever we do the experiment, the influence of the Earth's magnetic field is always there. So to avoid the effect of the Earth's magnetic field in the experiment, we are going to keep this coil in the north-south direction. Okay, otherwise the Earth's magnetic field will affect the deflection of the compass needle. That is the answer. 8th question. In the split ring commutator of a DC motor, semicircular rings are used. What is the need for this? So what is a commutator? We have seen that the brush, and this is how this commutator is connected, right? The commutator is connected and we have this rectangular coil, right? So rectangular coil will be connected here. It will be connected here. And so what happens is, if you connect this rectangular coil to the split rings, what is the function of a split ring commutator? The function of a split ring commutator is to reverse the direction of current, right? It is to reverse the direction of current in a circuit. So how this split ring commutator helps in reversing the direction of current? We know that the brushes and the rings P and Q and X and Y, the brushes are stationary and the rings, the split rings, will rotate. So we have the armature A, B, C, D, and the current initially, according to the explanation I have given in the class, this is the diagram, a rough diagram. So the current will be entering into the coil from A to B and comes out of the coil through CD, and this is the north and south pole of the magnet, right? So during every half rotation, the current in the arms of this armature should be reversed. That is possible only with the help of this half rings. If it is a complete ring, if you are using two complete rings here, the reversal of current in the arms AB and CD will not take place. Okay, so split ring commutator is a device which reverses the direction of current. So if it is complete ring, reversal of current will not take place in the armature. That is the answer for this question. Okay, so always the direction in the arms AB and CD of the armature should be reversed, so that we will be getting a continuous rotation in one particular direction. In this case, it will be anti-clockwise rotation. Hope you understood the function of split ring commutator. Now moving on to the 9th question. A current carrying solenoid is stretched to increase the distance between the coils. What change will occur in its magnetic field? Describe. So if you have a coil which is very close to each other, the coils are very close to each other, and if you just stretch it, right? So what happens? What is the difference between these two? If you stretch that, the distance between the coils, it's increasing. So when the distance between the coils is increasing, the number of magnetic field lines in that region, that goes away and away, right? That the distance between the field lines increases. That means the magnetic flux density will decrease. So what's the question here? What change will occur in its magnetic field? So we can say that the strength will be decreasing. Strength of the magnetic field, strength will decrease. Why? If the coils are very close to each other, then the magnetic field lines are very, very close to each other. And the strength of the magnetic field is determined by the degree of closeness of the magnetic field lines in that region. If you stretch this coil, if you make these coils away from each other, but see, we are making sure they are the part of the same coil, but the distance between the coil is increasing, then the magnetic field lines in that region, the distance between that decreases, and the magnetic flux density will be decreasing. So the strength will decrease. This is the explanation for this question. Now moving on to the last question. State the motor rule. If the direction of current in the conductor and the magnetic field are the same, in which way will the conductor move? What is the motor principle? A conductor which can move freely and which is kept in a magnetic field experiences a force when current passes through it and it moves. A current carrying conductor kept in a magnetic field will experience a force. That is a principle of a motor. And we can find out the direction of motion of this current carrying conductor using Fleming's left hand rule. Now, what is the next question here? In which way will the conductor move? What is the situation if the direction of the current in the conductor and the magnetic field are the same? In which way will the conductor move? So how do we find out the direction of motion of the conductor? By using Fleming's left hand rule. In Fleming's left hand rule, it says that we have to keep our left hand in the three fingers of our left hand in three mutually perpendicular directions, right? So if I'm taking, say this is field, current, and this is current, and this is the force or motion, right? But as per this question, they ask if the directions of current in the conductor and the magnetic field are the same. If the direction of current and magnetic field, that means current and magnetic field are in the same direction. So in this case, we can say that the deflection, the conductor will not move in that case. Okay, there will be no motion, no movement for the conductor. That's the answer for this question. No movement for the conductor, because the magnetic field and the current are in the same direction. Okay, so hope you understood the answers. Note down the questions and write it down in your notebook and learn the answers properly. So most of them are application based questions, so it's very, very important to know the rules and know the tricks. And the new thing I explained in today's session was the swimmer's rule, right? So always remember that the swimmer's rule is to find out the direction of magnetic compass needle deflection. Okay, so just take check the video once again and learn that rule also, because in this kind of application level questions we need that swimmer's rule. Okay, so the magnetic effect of electric current chapter is going to be done by today's session. And in the coming class, we will be discussing about electromagnetic induction. It is a very, very important and interesting topic. Okay, so if you're watching the video for the first time, just subscribe the channel and click the bell icon so that you get the updates whenever I upload a new lesson. Okay, so and try to watch the videos continuously so that you get the correct effect of doing these classes, because the maximum effect will be when you learn it regularly. Okay, so this was the text back exercises, and see you soon with electromagnetic induction concept. Thank you for watching. Bye.